welcome to today's chemistry class. Last class, we dealt with the concept of ionization energy, right? So, in the introduction, I'll leave the link to the introduction to IE in this video description, right? But today, we'll look at the introduction to IE. We'll look at the factors affecting ionization energy. In our last class, I said I'll be mentioning the word IE. So by IE, I mean ionization energy. So I won't call it in full, and I might call it in full. So you get to know as we study this concept. If you get the word IE, I refer to ionization energy. That's first things first. So last class we have done with the introduction and the trends, and because when it comes to this concept here, we have the first IE, second IE, and third IE. I've explained those things in our previous class, right? So the link will be given in the video description. So check the video description. You see a link that will take you to our previous class on introduction to IE. Let's move on from here. The next thing we're looking at is called the factors. What are these factors that are affecting IE? So look at the factors affecting IE. The factors that affect ionization energy. There are three in numbers, right? So this factor could be a reason why you have to increase or decrease IE, right? So the factors that affect IE are three. The first one that is called the atomic size and screening effect. Number one is called the atomic size, right? I will have and screening effect. All right. So this is your first factor that affects IE. Number two there, the second factor there is given as nuclear charge. Nuclear, of course, charge. And number three there, I have electron configuration of atom. Right. So that's the third factor. Electronic configuration right of the atom. All right, so these are the main factors, the three factors that affect ionization energy. Now, how do we get to understand this factor? What role they play to affect IE? Let's look at the rules this stuff play to affect IE. First things first, we said atomic size and screening effect. Obviously, this affects IE. Now, first things first, what's IE? In our previous class, I said it is the ability for an atom to lose an electron. We're saying this that it's possible for an atom to lose an electron when sufficient energy is applied to it. So it's possible to channel an energy to an atom if the energy is sufficient enough, is powerful enough, it could remove an electron from the atom, right? So here's the fact, please. The goal of IE is to make sure it looks into an atom and to remove an electron from that atom. That's the goal. It's looking for someone to distort, right? So here's the fact here. If I'm having this as a factor affecting IE, if you observe very well, if you observe some elements such as hydrogen, lithium, sodium, and potassium, the first one there. So before I explain the first one intensively, let's just write them down and see what I'm saying about atomic size and of course screening effect. All right. So we said for this one here, I said go back to your 20 element periodic table. If you check for this elements such as the arrangement of hydrogen, lithium, sodium, and potassium, if you observe this stuff, in the table, I will display it on the screen, right? So and I will show what I'm saying. That is, you will see what I'm trying to say. Display on the screen. If you observe the arrangement of hydrogen, lithium, sodium, and potassium, you observe that in this case, that as you because it's a matter of going down the group, right? So if I have a 20 elements, check properly, the arrangement of hydrogen, lithium, sodium, and potassium is more of like you are going down the group. And here's the technique here. If you observe hydrogen, if I draw the shell of hydrogen, of course it will have just one electron in the shell. If I draw the shell for lithium, it will have three electrons, right? So it means it will have an additional circle, right? It will have an additional circle, two circles. For sodium, it will involve three circles, which involve the K, L, and M shell, right? Similarly, for potassium, it will have probably three circles to four circles, depending on the case, right? So if you observe that the more you go down the group, taking hydrogen, lithium, sodium, and potassium, you observe that your shell keep increasing, the atomic size keep increasing. And here's the thing, the more it keep increasing, the far, or perhaps let's say, the farther the electron from the nucleus, right? So thereby, it will favor IE to come and play its role. So the goal is this: if your electron can be closer to your nucleus, it means that IE cannot easily remove an electron. But if the electrons in the nucleus are far from the nucleus, it is easy for IE to just remove an electron from that atom. That's the concept, please. So that's how IE affects atomic size and screening effect, right? So copy this down, please. First, IE decreases down the group because the greater the distance from the nucleus, the weaker the attraction and less energy is needed to remove an energy. So I've explained this concept. So let's look at number two, please. Number two, nuclear charge. Um, okay, so let's look at nuclear charge. What's a nuclear charge? All right, put on, please. Now, for nuclear charge, I think what we should look out for, the example we should look out to explain this better, if you check your arrangement of your second period, right? If you check from the period table, if you check the arrangement of lithium, beryllium, of course, boron, carbon, nitrogen, oxygen, fluorine, and of course, neon. If you observe the arrangement, this are they are in second period in the period table. This stuff here, right? If you check the arrangement, if you check from lithium, beryllium, boron, carbon, and etc., as shown on the board, if you observe properly, their nuclear charge are more closer to the nucleus, right? So put this down, please. Copy this down, please. The stronger attraction between the nucleus and the outermost electron requires more energy for removal, resulting in increase in IE. So here's the thing, please. If you observe the structure for all these elements here in the second period, you observe that they are closer to the nucleus, right? And here's the thing here. If you draw all these things here, the atomic size are not that big. They are consistent, right? They are consistent. They have a consistent pattern, right? So if you observe that the atomic shell are still more closer to the nucleus, so thereby the attraction becomes stronger. And in this case here, it will not favor IE because IE has to come with extra sufficient energy to be able to remove an electron from this element here. So here's the technique here. The further the electron from the nucleus, the easier IE can attack. But the closer the electron to the nucleus, the more energy, the more far IE needs to, remove an electron, and sometimes it's not possible. It's not be possible because the electron are closer to nucleus, thereby the strength, the bond is, of course, stronger enough to kick off IE. But IE, in the case whereby it needs to remove an electron, it means it needs to come with more energy, more and sufficient energy to kick off an atom. So it's not like this is like opposite a positive and negative explanation, like positive and negative explanation. Just understand how these two concepts works, right? And that's the second explanation to factor affecting IE. The third one there, number three, is given to be electronic configuration of the atom. All right. So in a case like this, for um, this case here, there are two conditions to this case, right? We have case one and case two. The first case is when you have a complete filled electron and of course an half-filled electron, right? So when we look at a completely filled electron, how does IE comes to play? An half-filled electron, how does IE comes to play? Now we said in this case here, you're having two categories. The first one is called the completely filled electron, completely filled filled and have the filled half filled sublevel sublevel. For the B part there, we have completely filled shell. All right, so all right, in this case here, they are noble gas. Noble gas are referred to as complete filled shell. So noble gas has a complete filled shell, right? So these are the two categories involved in the concept of electronic configuration of the atom. There are two. Now these two, how do we get to understand them? How do they work? Now let's explain the first one, A. So let's explain A, please. For A, properly that A indicates completely filled and half filled, right? So if you have a completely filled electron and a half filled electron, what comes to mind, please? Put this down, please. Put this down. Put this down, please. Note, please. You know what? Okay. Put this down, please. Orbitals that are completely filled or half filled. Please note under this, please. Under the first one, orbitals that are completely filled or half filled, it is difficult to remove an electron from them. I said orbitals that are completely filled or half filled, it is difficult to remove an electron from them. Why is it so? If you observe magnesium, phosphorus, um, aluminium, silicon, phosphorus, from sodium to argon, if you observe the pattern, right, from sodium to argon, you observe that the increase in first IE is irregular, right? For example, if you have magnesium and phosphorus, right, if you observe these two elements are having a um higher, what's it called, stability, right? So if IE is coming to play in this case, it needs sufficient energy. So in other words, it is safe to say that when it comes to completely filled or half filled, that it is not easier for IE to what there remove an electron. As I said earlier that orbitals that are completely filled or half-filled, it is difficult to remove an electron from them. So that's the key thing to take here from here. The key take here is that orbitals that are completely filled or half-filled, it is difficult to remove an electron from them. That's how you get to understand the first category on the third factor affecting IE. Okay, third example. Next up, please. The second one there is called the completely filled shell, and you said completely filled shell are your noble gases, right? If you check your periodic table, the one at the extreme, I'll display the image and I will indicate. I use an arrow to indicate what I'm saying, right? So if you've got the noble gases, they are the only elements in the in the first element that have a stable atom, right? Their shell is stable, and we said the stability of an atom is determined by two factors, either its duplet or what there or octet configuration. By duplet, we mean it will have just two valence electron in the outermost shell, right? Please, all this English I'm saying, if you don't get it right, one learn chemistry from start, right? I have a full playlist for chemistry, inorganic chemistry to be precise, right? I have the videos arranged in order. So if your head is blank in chemistry and you want to learn from the beginning, from the start, I have an order of arrangement of video that will help you attain that um, knowledge, right? So you can just get check my channel to have access to the chemistry video from start, right? So if okay, I'll leave the link. Perhaps I might leave the link to the video to this video description. So check it. You see a full playlist, right? Playlist. It's when I say playlist, what I mean is a particular link where you have access to videos arranged in accordance, right? The first what to watch before the second one, before the third one, right? So I'll leave the link to this video description. So I'm saying is that the stability of an atom is determined by two things. So why is noble gas stable? Because of two things. Because in their shell there might be either duplet or octet. So these two things are occur in your noble gases. That is why we call them a stable atom, right? So for a stable atom, that's why I indicate that is your what's it called? Noble gases are refers to as completely filled shell. In a case like this, what do you need to take out of this place? What you take out of this is to note that note please under this place note noble gases note please noble gases have completely filled outermost electron shell, making them very stable. All right, making them very stable. A much higher energy is required. A much higher energy is required to remove an electron. I said a much higher energy is required to remove an electron from a completely complete shell. To remove an electron from a complete shell. This is your key take when it comes to the second, what's it called? The third factor, and that's like the second category to the third factor affecting ionization energy. This is basically the full tutorial to IE. The first tutorial was the introduction to IE, where I explained what IE means and the first IE, second IE, and I explained that in our previous class. The link will be given to you in the video description, right? Number two is that this is the end of IE. Now we'll now solve several past questions involved in the study so we can refresh our mind on what we have learned in our previous class and now. Let's look at a few past questions in the study of um, IE in general. Question 1 says, welcome back. So let's proceed with several past questions in the study of ionization energy, in quotes, aka IE, right? So persons first. Question 1 says, in order of remove, in order to remove this, in order to remove an electron from a 3x orbital of a gaseous sodium atom, about 496 kilojoule per mole of energy is required. This energy is referred to option A, electron affinity, option B, ionization energy, option C, activation energy, option D, electronegativity. Now listen and listen. Get the whole idea of the question. It says, in order to remove one electron from the 3x orbital of a gaseous sodium atom, I am removing an electron from a gaseous, please, that element is in gaseous state, and we said, i.e., the element must always be in gaseous state. Now in this case here, sodium is in gaseous state. Okay, I am satisfied with it. Next up there, it says you are reached to remove one electron from what? A gaseous sodium atom, right? So what kind of energy is required? That's like the concept there. Of course, my answer is what there? Option B, i.e., that's it, please. That's how it works, please. So because in this case here, they give us sodium, right? Sodium in a gaseous state, right? And they gave us, of course, to remove just one electron from this sodium atom in gaseous state. So what energy does the remover? Of course, is what there, i.e., its goal is just to remove electron from an atom. So of course, my answer is option B is my answer in this case. Question 2. Question 2 says, what happens to the ionization energy of elements as you move down a group in the periodic table? This question, if you want to answer this question, you must have watched our previous class. That's introduction. This one you're talking about the trends of IE, right? We said across the period, IE increases. Down the group, IE decreases, right? In this case, it was saying what happens to IE of element as you move down the group. So in the table, so as you move down the group, check your previous class, check the note there. We said, i.e., as you move across the period, it increases. Down the group, it decreases. In this case here, option A says it increases, option B says it decreases, option C says it remains the same, while option D says it increases then decreases. Obviously, my answer here is option B. So this is how I solve problems under the concept of ionization energy. Moving on, please. Question 3. It says, which of the following correctly define the first ionization energy? It says, which of the following correctly define the first ionization energy? Please, this question, you can't answer it if you only watch this particular class. You must have watched our previous video. I'll leave the link in the video description. Please don't say you just watch this and you cannot solve this problem. Check up, watch the full class so to better understand what we are teaching here, right? So what it says, which of the following correctly define the first IE, right? That's another energy. Option A says the energy required to add, i.e., it removes. So yeah, this option is not even part of my answer. It says which of the energy is required, the energy required to add an electron to a neutral atom in a gaseous state. That's not the answer, please. That's not it, please. Option B says the energy required to remove one electron from a neutral atom in a neutral state. Makes sense. Okay. Option C says the energy required to remove an electron from a singly charged ion. Okay. Option D says the energy released when an electron is added to a nuclear atom in a gaseous state. Obviously, my answer here technically is option B. Why? Because option B says the energy required to remove one electron from a neutral atom in a gaseous state. That's how you define your first ionization energy. So that's the answer. Option B is the answer here. So you take this as assignment for me. Leave your answer in the comment section of this video. So take this assignment. Leave your answer in the comment section of this video. It says, come in. It says, which factor does not affect ionization energy? Please listen. I just discussed that now. It says, which factor does not affect ionization energy? Option 1 says atomic radius. Option 2 says nuclear charge. Option 3 says electron shield, electron shielding. Option D says number of neutron. Please, which of them is your answer? Leave your answer in the video, in the comment section of this video. That's your assignment number 1. Assignment number two says, which is the general trends for successive ionization energy? Which is the general trends for successive IE, in brackets IE1, IE2, IE3 in an atom? Now, if you check this properly, if you check your third IE, I gave you a conclusion, right? I gave you IE1, IE2, and IE3. So there was a symbol there of greater than or less than, right? So you have to pick which one correspond with the pattern of your first and second and third IE. Option A says, okay, I'll leave the options on the screen. So you pick your answer and leave your answer in the comment section of this video. Two assignments. The first one, answer in the comment section. The second one too, leave your answer in the comment section and also put your location where you are watching from. Let us know in the comment section of this video. So see you guys in the next video where we'll look at the concept of electron positivity. If you enjoyed this class, do well to like this video, leave a comment, and also subscribe to this channel. Right? I have a WhatsApp group where students are there globally. Right? So you can also join this WhatsApp group. I'll leave the link to this WhatsApp group in the video description. Right? So you can reach out to me through WhatsApp number or through the link I'll leave in the video description. So always try to check my description. I usually you put updates there, so you have access to several updates in the video description. So see you guys in the next video, and welcome to Excellent Link Academy.